Hey there! Today we're going to build your very first integration toolkit. So if you've ever wondered how you go backwards from a derivative, you are in exactly the right place. We're going to break down all of the essential rules so you can start tackling integrals with some real confidence. Let's get right into it.
Okay, so you've probably spent a ton of time learning how to take a function and find its derivative, right? It's kind of like taking a car apart to see exactly how all the pieces work. But what if I gave you all the parts and asked you to build the car? Well, that's integration. It's the challenge of going in reverse.
The secret to going backwards is this idea of an antiderivative. And honestly, the concept is pretty straightforward. If you can find a function, let's call it big f of x, whose derivative is the function you started with, little f of x, then congratulations, you found the antiderivative. You've just gone backwards.
Just look at this comparison. On the left, taking the derivative of x squared to get 2x, easy. We've got clear rules for that. But look at the right. How do we get from 2x back to x squared? That's the puzzle we're here to solve. We need a whole new set of rules, not for breaking functions down, but for building them back up.
So, that brings us right to our first section. We are officially taking on that reverse challenge, learning the fundamental techniques to put these functions back together again.
First things first, let's talk notation. That long s symbol, that's the integral sign. It's basically asking, what's the general antiderivative of this function? Now that plus c at the end is super important. Think about it. The derivative of x squared is 2x, but the derivative of x squared plus 5 is also 2x. So is x squared minus 100. That plus c, the constant of integration, is our way of saying, hey, there could have been any constant here before we took the derivative. It's a crucial detail you can't forget.
All right, it's time to add the first two tools to our new toolkit. These are the absolute basics, the bedrock for everything else we're going to do.
Let's start with the simplest thing imaginable, the integral of a constant, which we'll call k. We know from derivatives that if you have a function like kx, its derivative is just k. So if we work backwards, it just makes sense that the integral of k has to be kx. And of course, we tack on our plus c. And just like that, our first rule is in the bag.
Now for the real workhorse of basic integration, the power rule. Remember how with derivatives, you brought the power down in front and then subtracted 1 from the exponent? Well, here we do the exact opposite. First, you add 1 to the exponent, and then you divide by that new exponent. It's the perfect reversal of the derivative process.
And this is so cool because it shows that this isn't just some abstract symbol game. When we integrate the simple function y equals x, the power rule gives us x squared divided by 2. And what's that? It's the formula for the area of a triangle. It shows that integration is deeply fundamentally connected to the idea of calculating area.
So we have our first couple of tools. That's great. But what about more complicated functions? What happens when things are added together or multiplied by numbers? Well, our next set of rules is going to show us exactly how to handle that. Okay, this theorem looks a little formal, but what it's telling us is actually a huge game changer. It basically says two really simple things. One, you can break an integral of a sum into a sum of separate integrals. And two, if you have a constant being multiplied, you can just pull it right out in front of the integral sign. This is huge because it lets us take complicated problems and break them into smaller, much more manageable pieces.
So how do we actually apply this? I mean, handling a single term like x squared is one thing, but what about a full polynomial like this one? It looks a lot more intimidating, right? Where would you even begin?
We use the rules we just learned. That's how. First, the sum rule lets us split this big problem into 3 separate, much friendlier integrals. Then, the constant multiple rule lets us pop the 3, the 5, and the 2 right out front. And look what we have left. 3 simple integrals that we already know how to solve using our power and constant rules. We just turned a scary problem into a totally straightforward one.
Our toolkit is looking pretty good right now, but there's a catch. There is one very specific case where our most powerful tool, the power rule, completely and utterly fails us. Let's find out why.
So, take a look at this. What happens if you try to integrate 1 over x? Well, as the hint says, that's the same thing as x to the power of -1. So go ahead, try to apply the power rule to that. What happens?
And there it is, complete breakdown. If you add 1 to the exponent, -1 plus 1 is 0, then when you try to divide by that new exponent, you're dividing by 0. The power rule just doesn't work here. We need a different tool for this job.
And here is that classic aha moment. The solution doesn't come from the power rule at all. It comes from just remembering a different derivative we already know. We know that the derivative of the natural log of x is 1 over x. The answer was hiding in plain sight the whole time.
And this gives us our last tool for today, the natural log rule. The integral of 1 over x is the natural log of the absolute value of x plus c. And that absolute value is important because you can only take the log of positive numbers, but the original function, 1 over x, works just fine for negative numbers too.
Awesome. We've collected all of our basic tools. So for this final section, let's lay them all out on the workbench and see our brand new toolkit in action. And here it is, all in one place, your foundational integration toolkit. You've got the constant rule, the power rule, the rules for sums and constant multiples, and our special case, the natural log rule. With just these 5 rules, you can solve any polynomial and a whole bunch of other common functions. This is your starting lineup.
Okay, let's run through one last example to see it all come together. We start with the difference rule to split it into 2 problems. Then we pull out the constants, the 4 and the 5. The first part is a job for our trusty power rule. The second part is a perfect fit for our new natural log rule. We solve each piece, simplify it down, and we're done. A problem that looked kind of complex is solved systematically with our new toolkit.
We've built a really powerful starter kit today. We can handle things being added, subtracted, and multiplied by constants. But what about multiplying 2 functions together? Our rules work for adding, but what happens if you have something like x times e to the x? Well, that's a puzzle for another day and the very next step on your integration journey.